Welcome back, and in this class we will discuss about thermal processing and heat treatment of steels. So, let us have a quick looking back at phase diagrams. So, what we have discussed in the phase diagrams. So, in the discussion on phase diagrams, we primarily paid attention to the information about the temperature and composition, right. So, we have discussed at a for a given composition of an alloy, when we are cooling it down, how the microstructure evolves. However, we have not actually discussed anywhere during the discussion of phase diagrams what is the time that is required to convert a liquid phase to a solid state, and at each and every instances how long should I wait at a given temperature in order for the transformation to complete. So, the issue of time is not discussed anywhere during the discussion on phase diagrams. However, time plays a critical role in the microstructure evolution of the alloy of any composition that we are looking at, for instance in a binary phase diagrams. And we have actually had a discussion on the effect of time for one specific case, when we have discussed the non-equilibrium cooling of isomorphous alloys, where we have shown that the microstructure that is developed during non-equilibrium cooling of an isomorphous alloy is different from the microstructure obtained through equilibrium cooling. So, the major difference between equilibrium cooling and non-equilibrium cooling is the time involved, or that amount of time that one is that we are providing for the system to cool down at a given temperature, right. And hence, the time is the key for the real microstructure evolution during the solidification. So, in this module we will pay attention to this aspect of time, and then understand how the microstructure evolution is going to get affected because of the time that is involved during the transformation. So, the learning outcomes of this module are, so first we will discuss about the fundamentals of this microstructure evolution. So, the microstructure evolution from liquid state to solid state is governed by the two phenomena, one of the important phenomena called nucleation and followed by growth. So, we need to understand different types of nucleation during solidification. So, we should be able to define different types of nucleation during solidification. So, for the case of homogeneous nucleation, we will be deriving the expression for critical radius r star of a nucleus or embryo, and activation free energy delta G star, and the nucleation rate n dot. It is not n star, it is n dot. And we should at the end of this module we should be able to list the differences between homogeneous nucleation and heterogeneous nucleation, right. And also we should be able to write the relation between the activation free energies of homogeneous nucleation and heterogeneous nucleation, how their activation free energies are related. And then we will talk about an important concept called isothermal transformation diagram, and then while we are talking about isothermal transformation diagram, we should be able to list various experimental steps that one needs to undertake in order to generate such an isothermal transformation diagram. And we should be able to draw the isothermal transformation diagram for eutectoid plain carbon steel and hypo and hypereutectoid plain carbon steels, and identify the microstructure of plain carbon steel obtained at different cooling rates. That is the key. So, the time is coming here, and then we will be able to see when we have different cooling rates how the microstructure is evolving. Okay, so, to begin with, we will study about this kinetics of phase transformation. So, what are the when we are talking about phase transformation, which actually essentially means two aspects. The first, you should have nucleation of the product phase. So, you have a liquid phase to, let us say, solid phase transformation. So, this liquid phase is called parent phase and solid phase is called product phase, if your phase transformation is happening from liquid state to solid state. But as we have seen in the discussion on phase diagrams, we also have seen phase transformations happening within the solid state. For instance, eutectoid reaction and peritectoid reaction, these are the transformations that are happening within the solid state. That means, your phase transformation need not always happen from liquid to solid, but it can also happen within solid state, right. So, if it is happening from solid state 1 to solid state 2, then this is what is called our parent phase and this is our product phase, right. So, when we are having the transformation from a parent phase to product phase, during this transformation at an appropriate temperature, you have the nucleation of the product phase system. So, right, so for instance, whenever we are solidifying a liquid, the nuclei of solid should form at the freezing temperature or solidification temperature, right. So, when we are talking about nucleation, there are two kinds of nucleation. First one is homogeneous nucleation and heterogeneous nucleation. So, what do we mean by homogeneous nucleation? So, if the if the nucleation sites for the new phase that are, let us say in this case solid phase, form uniformly throughout the parent phase. That means, if you have, say, let us say this is our liquid, here the nucleation of the solid phase should happen uniformly throughout the parent phase. So, then such a nucleation is called homogeneous nucleation. That means, there should not be any preference for the nucleation, preference of any site, there should not be any preferential sites for beginning of the nucleation. Such a nucleation is called homogeneous nucleation. Heterogeneous nucleation is nothing but the nucleation of new phase happens preferentially along certain geometric features, such as, for instance, if you are solidifying a liquid metal in a crucible. So, the crucible surface may be one of the favorable positions where nucleation can begin, right, or sometimes you may have inclusions. So, inclusion surfaces can be a favorable nucleation sites. And similarly, if you are dealing with if you have a system where you have certain amount of liquid has already transformed to a solid and already there may be some dislocations and grain boundaries that are generated, they can also be states of heterogeneous nucleation. But within solid state, if you have transformation from one solid state to another solid state, the grain boundaries and nuclear dislocations can act as preferential sites for nucleation. So, in principle you can have these two kinds of nucleations, homogeneous and heterogeneous nucleation. And once the nucleation of a product phase begins, then this nucleus has to grow in order to finish the complete transformation. So, the next stage is growth stage, right. All right. So, now let us try to understand or spend some time understanding homogeneous nucleation and derive certain important expressions that we have discussed in the learning outcomes. So, as we have already mentioned, the homogeneous nucleation refers to the formation of nuclei of new phase or product phase uniformly throughout the parent phase. So, there is no preference whatsoever for the location where the nuclei has to form. So, for instance, here we are in this discussion we will be discussing about the phase transformation from liquid state to solid state or within solid phase. But the discussion that we are having can be applied to any phase transformation, any other phase transformation from one state to another state. And as we the phase transformation depends on an important thermodynamic property called change in free energy. Okay. So, whenever a phase transformation is occurring from one state to one phase to another phase, such a transformation occurs only when there is a reduction in free energy. What is the meaning of that? So, if you have at a given temperature a liquid is transforming to solid, that means the solid's free energy is less than the liquid free energy. So, the delta G is equal to G s minus G L, that should be less than 0. So, always your phase transformation happens from one phase to another phase only when the change in free energy is negative. Okay. So, now let us try to look at the solidification of a pure metal under homogeneous nucleation. So, assume that this gray area that I am showing here is our liquid, right. So, now let us assume that the nuclei of solid phase, we are paying attention to one nucleus, but there are several such nuclei formed uniformly throughout the liquid phase because it is homogeneous nucleation, but we are paying attention to one such nuclei. Assume that the nuclei of solid phase form within the interior of the liquid. So, if you have a liquid pool, you are assuming that the solid phase is nucleus is forming within the interior, it is not forming on the boundary. Okay. And we are assuming that the solid phase is the nucleus is having a spherical shape. That is an assumption, but the methodology that we are developing can be applied to any other shape too. But to make the discussion simple, we are going to assume the nucleus to be of spherical shape. So, assume that the nucleus is spherical shape with a radius r. So, as shown in here the blue color, this is our nucleus or solid. So, this is our liquid, the gray color region, and this blue color region is solid nucleus, and then this line, the boundary, the circumference of this circle. So, it is shown in 2D, but it is a sphere. Okay. And this is the solid liquid interface. And if you have a solid of sphere of radius r, then the volume of this sphere is 4/3 pi r cube, and the surface area is a is equal to 4 pi r square. All right. So, now when we have a system like that, there will be two contributions to free energy change. First contribution is the free energy difference between solid and liquid phases, right. The free energy difference between solid and liquid phases, which is going to be negative, then that is what we are calling volume free energy. So, delta GV is called volume free energy, which is negative if at all the phase transformation is happening, because the difference between the free energy between the solid and the liquid phase has to be, so solid phase free energy should be less than the liquid phase free energy. So, the free energy difference between solid and liquid phases is called volume free energy, represented by delta GV. Right. So, the contribution from solid liquid phase boundary again, so there should be another one contribution is from the volume, another contribution is coming from the boundary or surface during the transformation, that is called surface energy. So, the total free energy change is equal to volume free energy plus surface energy. So, the volume free energy is nothing but volume times free energy change. So, that is 4/3 pi r cube is the volume of this sphere, and free energy change or volume free energy is delta GV, and your surface energy change is actually 4 pi r square, because before that there is no surface. Now, you have surface energy and gamma is the 4 pi r square is the surface area, and gamma is the surface energy associated with the interface boundary between solid and liquid. So, this is the total free energy change delta G, represented by delta G. All right. So, now if you would plot the two quantities, that is volume free energy and surface energy, and the total quantity, note that this is a negative quantity and this is positive quantity. So, you can see that this blue dashed line is our surface energy term. So, 4 pi r square gamma, and the black dashed line is our free energy, volume free energy term, and now the sum of these two is described by this red line, red solid line, which actually shows a maximum and then decreases, right. So, the maximum value of delta G, after which what is happening? So, up to here the free energy is increasing and then it is decreasing. However, here please note that this free energy total delta G is plotted as a function of radius of the particle or radius of the nucleus. Okay. So, you have a free energy change has a certain feature which is increasing first and then decreasing. Let us try to understand what is the meaning of that. So, we see that the total free energy change increases, passes through a maximum and then decreases. So, this trend of delta G physically implies that the free energy increases as a solid particle starts to form through the clustering of the atoms in the liquid. So, what happens when the solid particle is starting to form, the atoms from the liquid state should be coming together and to be clustering to form a nucleus, right. So, when such a process is happening, the free energy change, the delta G is first increasing and then decreases. So, if the cluster size reaches a critical radius r star, as we have seen here, if the cluster size is this distance r star, it will continue the nucleus. So, is that will continue to grow as the free energy now starts decreasing thereafter. So, if the nucleus size becomes equal to r star, so the clustering of atoms of liquid state to form solid state, from the liquid state to solid state reaches a critical size called R star, that is when the nucleus continues to grow, because after R star the delta G starts decreasing. However, if the cluster radius means the radius of this cluster of atoms which are trying to form a nucleus is less than the critical radius, then what happens, because it is not energetically favorable, then it will shrink or dissolve. It cannot it cannot be stable, because energetically it is not favorable, because if it is less than R star, further increase will actually make it increase of free energy, which is not total free energy is increasing, which is not energetically favorable situation. So, the subcritical particle with radius less than R star is called embryo. So, that means if your particle size is less than R star, then it is embryo, which will eventually dissolve or shrink, and the particles with radius greater than R star are called nucleus. Okay. So, the free energy change at the critical radius R star, as we have seen here, at this critical radius the free energy change is delta G star. So, the free energy change that corresponding to the critical radius R star is what we call critical free energy change delta G star, or it is also called activation free energy, and that is important, right. So, the activation free energy is the free energy change at the critical radius R star, when the radius radius of the cluster of atoms reaches your critical radius R star. Okay. So, now the free energy required for the formation of stable nucleus is what we call activation free energy, right. So, this is the free energy change that is required in order to form a stable nucleus. Otherwise, the nucleus will be unstable and then it will again dissolve. So, the delta G star, so we know what is we have seen what is G as a function of R. Now, let us find out what is the so the delta G star corresponds to the maximum value of G delta G as a function of R, right. So, we can find the derivative of this delta G with respect to R and then equate it to 0 in order to find the maximum value, and we do that, then we get R star is equal to negative of 2 gamma by delta G V, where gamma is the surface energy, delta G V is our volume free energy. So, it basically the radius, the critical radius depends on the surface energy and the volume free energy of the system. And what is the critical free energy change or the activation free energy is basically 16 pi gamma cube by 3 times delta G V whole square, as we can solve this equation to get the R star and then plug in R star back, then you will get delta G star total you solve this equation to get R star and then plug in this equation into the equation of delta G is equal to 4 pi R square delta G V time plus 4 pi R square gamma plus 4/3 pi R cube delta G V, as we have seen before. So, the driving force for the solidification is actually your volume free energy delta G V, right. So, if you have less activation free energy, then it is much easier for the formation of nucleus. So, the magnitude of the delta G V. So, as we the delta G V is our volume free energy. So, the magnitude of this volume free energy is a function of temperature and latent heat of fusion. What does this depend on? The magnitude of volume free energy change in delta G V is our volume free energy. It depends on the temperature and the latent heat of fusion, which is defined by delta H f. So, now I can replace my delta G V using this expression, the relation between delta G V and latent heat of fusion and temperature, where T m is the solidification temperature or melting temperature, T is the temperature at which we are measuring or we are actually trying to find out what is volume free energy. So, volume free energy is a function of temperature. So, at the solidification temperature, right. So, at the solidification temperature, that means T m equal to T, the delta G V becomes 0, and beyond that. So, suppose if you reduce T value below the solidification temperature, we know that delta H f is negative because it is latent heat of fusion, that means it is heat not supplied, but heat is given by the system and hence it is negative, and hence it becomes more and more negative, right, as you are reducing. Suppose let us say is our T m, and if you reduce your T, if you are making your T farther away from Tm, then this delta GV becomes more and more negative. So, at solidification temperature it is 0 and continues to be more negative as temperature decreases further. Temperature means this T. Alright. So, now we can write our R star and delta G star in terms of latent heat of fusion and temperature, and you can clearly see that. So, R star is a function of, is written as a function of gamma, Tm, delta Hf and the temperature, same is delta G star. And note that the quantities, the surface free energy gamma and latent heat of fusion delta Hf, these two parameters are usually less sensitive to temperature change. They are sensitive, but they are not very strong functions of temperature. So, they are very less much less sensitive to temperature change. Implies that your R star and delta G star, by looking at the way that this expression is, we can say that both R star and delta G star, assuming gamma and delta Hf are constants, they do not change with temperature, then we can say that as you reduce your temperature T, R star and delta G star also reduces, right, because as you are reducing this number, this difference increases, as a result this fraction reduces, and hence you will have lower value of R star. So, if you would plot the R star and delta delta G as a function of temperature. So, in the expression where you have delta G is equal to 4/3 pi R square delta G V plus 4 pi R cube, 4 pi R square gamma, you replace delta G V with the expression that delta Hf times Tm minus T divided by T, right. So, and then we can find the expression for delta G, and then we can plot the delta G as a function of R for different values of temperatures, because here the delta G now can be written as a function of temperature, temperature, and then we would be able to plot delta G for different temperature values. So, here I am plotting, so let us say Tm is somewhere up here where your delta GV is 0. So, Tm is somewhere up here, this is, let us say this is my this is not temperature, I am sorry, this is delta GV. Now, if I am plotting delta G as a function of R at two different temperatures where T2 is greater than T1. So, T1 is smaller. So, if you are on the T scale, if this is my Tm and that is, let us say T2 and that is my T1. So, T1 is smaller than T2 and T2 is smaller than Tm, right. Then we can clearly see, as you are reducing the temperature, your R star, R1 star and R2 star. So, you can see that R1 star is less than R2 star and delta G1 star is less than delta G2 star. So, at lower temperatures it is much easier for the nucleation to happen, right. If your temperature is far away from the freezing temperature, then the radius, critical radius is less and the activation free energy is also less, and hence the solidification. So, the nucleation happens more readily at temperatures farther from the solidification temperature or temperature far below the solidification temperatures. So, if the temperature is farther from Tm, the nucleation happens easily. So, that is what we are trying to say. If the temperature is less than the solidification temperature, then it is easy to start nucleation. And so, you are talking about we have focused so far our attention to the nucleation of one particle, but the number of, so because we are talking about homogeneous nucleation. So, the number of such stable nuclei n star, which is, whenever say we are saying stable nuclei n star, that means for all these n star nuclei the radius is greater than R star, that also depends on temperature. Okay. So, the n star can be expressed as a function of delta G star and the temperature, right. For a given temperature we know what is the delta G star, and as a result, as you are reducing your so you can see that here n star you know that delta G star is also a function of temperature and T is also another factor. So, this N star, as you know, with reduction in temperature, the delta G star reduces, right. So, but with reduction in this term in the exponential has the effect of temperature on the numerator as well as on the denominator, right. So, if you reduce the temperature, this entire quantity is increasing, or if you keep delta G star constant, right. So, let us carefully look at it. So, if you are, let us say we are saying that delta G star is constant, which it is not, normally it is function of temperature. Let us, for the sake of argument, let us say delta G star is constant, then as you reduce the temperature, this fraction increases. So, as you reduce the temperature, the fraction increases. Okay. Now, let us forget about the effect of temperature. Now, we know that as you reduce temperature, the delta G star reduces, right. So, now you have two terms on the numerator term with as an effect which is opposing the effect that is caused by the denominator term, right, because the temperature also going to affect and delta G star is also a function of temperature. So, the effect of temperature, however, is larger on delta G star. So, the effect of temperature on delta G star is larger than the temperature term in the denominator, and hence with the reduction in temperature below Tm, their exponential term decreases, that means this term decreases, but it is a negative, there is a negative here, and as a result the number of stable nuclei N star increases. That means, as you go away from the solidification temperature, as you go down, the number of stable nuclei also increases, like the nucleation is easier and the number of stable nuclei also will be more as you go away from the solidification temperature. That means, if you have, okay. So, that is the concept that we need to understand, that the number of stable nuclei also increases as not also, number of stable nuclei increases as you reduce the temperature from the solidification temperature. All right. So, another important aspect during this nucleation is we need to see, we know that the nucleation happens by clustering of atoms within the liquid state to form a solid nucleus, right. So, the clustering of atoms happens by short range diffusion, which also influences the nucleation process. So, that means we need to also take into consideration of the fact that how many nuclei, how many atoms are coming and attaching to the already clustered solid surface and so on. So, the effect of this short range diffusion, so the effect of diffusion can be related to the frequency of atoms joining the solid nucleus from liquid. So, that basically represents the short range diffusion in the of the atoms for clustering. And so, this is basically described by the frequency of atoms joining the solid state from the liquid state, and this frequency is designated by Vd. The d is to represent diffusion. So, this can be expressed similar to our diffusion coefficient. So, the similar expression can be written here. So, here K2 times e power minus q d by Kt, where the influence of temperature on the frequency of atoms joining the nucleus and the diffusion coefficients are similar as shown by this equation, and Qd is our activation energy for diffusion and K2 is a temperature independent constant, and small k is our Boltzmann constant and T is temperature in absolute Kelvin. All right. So, now if you would plot, so the nucleation is dependent on both the stable number of stable nuclei and also the clustering or the frequency at which the atoms from liquid state are coming and getting attached to the solid nucleus, right. So, if you would plot this number of stable nuclei N star and the frequency of attachment V d, they are having mutually opposing effects, right. At high temperatures the nucleation is low. So, on the x axis we are showing nucleation. So, at high temperatures it is low, whereas at high temperatures the diffusion or the frequency of attachment is high, all right. And now let us now define another term called nucleation rate. So, what do we mean by nucleation rate? So, the number of nuclei formed per unit time is what is called nucleation rate, designated by n dot. So, this nucleation rate is proportional to the number of stable nuclei and the diffusion rate, or the frequency with which at which the atoms from liquid state are coming and attaching to the solid state. So, it is proportional to n star and V d. So, I can write n dot is proportional to n star times V d, and as a result I can write then n dot equal to k 3 is our proportionality constant times n star times V d. And now I can write what is n1 n star and V d. N star is k 2 times e power minus delta g star by k t, and V d is k 3 times e power minus q d by k 2 times e power minus q d by k t, right. So, here the k 3 term, that is our proportionality constant for nucleation rate, represents the number of atoms on the surface of the nucleus, all right. So, this is our nucleation rate. Now, let us plot how the nucleation rate changes as a function of temperature. So, on the y axis we are showing temperature, on the x axis we are showing the green curve, this is our nucleation rate, and this we have already plotted, but we are plotting it on the same graph. The n star is the number of stable nuclei as a function of temperature, and the diffusion or the frequency of attachment of atoms as a function of temperature. As you can see, n star increases as you decrease the temperature, V d decreases as you decrease the temperature, right. As you are decreasing the temperature, V d decreases. The combined effect, so the product of these two things is what we are calling nucleation rate, and this is shown by the green graph, wherein the nucleation rate, as you are reducing the temperature, the nucleation rate starts increasing and then reaches a maximum and then decreases, right. So, the maximum value of this nucleation rate will happen approximately when the number of stable nuclei n star and V d will be equal. So, around this temperature where they are meeting, around the same temperature you will have maximum value of nucleation rate. So, the upper region of this nucleation rate curve shows a steep increase. You can see that there is a steep increase in the number of in the nucleation rate, steep increase in the nucleation rate with a decrease in delta t. So, what is this delta t? Delta t is the temperature difference between the solidification temperature and the temperature at which we are calculating the nucleation rate. And as you are increasing this delta t, or as we are decreasing the temperature, both are same, your nucleation rate first increases. So, as we know, at high temperatures, as we can see, diffusion is dominant, and at low temperatures nucleation is dominant. So, obviously the nucleation rate reaches a maximum where diffusion and nucleation rates are almost equal, and the lower region is controlled by nucleation, upper region is controlled by diffusion, and are limited, or the lower region is limited by diffusion, upper region is limited by nucleation, number of stable nucleation. So, the methodology that we have discussed so far can also be not necessarily applicable only for spherical nucleus, it can be applied for non-spherical nuclei also, and it can also be applied to other phase transformations like solid vapor, solid solid, and so on. And note that in this previous graph, the appreciable amount of nucleation, so up to here, up to this temperature away from Tm, you do not have a reasonable appreciable amount of nucleation rate. The nucleation rate starts picking up after certain temperature below our freezing temperature, right. So, the appreciable nucleation rate starts only at a temperature below solidification temperature Tm, and the process of bringing the temperature below the solidification temperature for creation of nucleation is called supercooling or undercooling, and the temperature by the amount of temperature by which we are reducing the temperature from the solidification temperature is what we call degree of undercooling or degree of supercooling. All right. So, for several metals, the degree of supercooling could be of the order of 100 degrees Kelvin. For several metals, for homogeneous nucleation, if you would calculate, so the degree of supercooling would be around few hundred kelvins. So, we can see what is this, the delta T that we are talking about is the degree of supercooling. So, this table here shows the degree of undercooling for several metals. For instance, if you take iron, so you need to for the nucleation rate to have an appreciable number, you need to undercool iron, pure iron to almost 300 degrees Kelvin or 300 degrees Celsius. So, it is few hundred degrees Celsius.